Hi, my name is Igor Bascandziev, and I'd like to thank you for joining this presentation titled Inconsistencies Among Beliefs as a Basis for Learning by Thought Experiments. Let me start by saying that the human conceptual repertoire is unique in the natural world. Consider these several examples of concepts, some of which are embedded in and get their meaning from rich theories about the world. The concept of infinity, the concept of treason, as represented here by the painting The Death of Caesar by Camuccini, and concepts that undergo change as a result of theory change. For example, the concepts of life and death that undergo change in early childhood, and the concepts of force and motion that get different meaning under the impetus theory of motion as compared to the Newtonian theory of classical mechanics. These concepts are not available to other animals or to young children. They have been constructed over historical time, and they're constructed anew by individuals over ontogenesis. Importantly, some of these concepts undergo change as a result of theory change, such as the concepts of life and death and the concepts of forces and motion, the latter being the focus of this talk. But why do learners revise theories in the first place? Obviously, receiving new input from other people and from the world would lead to learning. Indeed, we know from previous studies that concurrently produced data that are inconsistent with prior beliefs helps learning. It leads to more explorative behaviors and more explanations. However, a somewhat neglected aspect is that learners, just by virtue of living in a world that does not agree with their naive theories, will necessarily have experiences and knowledge and beliefs that are inconsistent with their incorrect naive theories and naive beliefs. What's not clear, however, is whether the pointing out the inconsistencies between beliefs stemming from naive theories and beliefs stemming from other experiences via thought experiments and without the provision of new data would lead to learning. Thomas Kuhn proposed that theory change and conceptual change could be, and indeed have been, motivated by thought experiments in the history of science. He noted and documented many examples of thought experiments, again in the history of science, that yield contradictory conclusions. And according to Kuhn, such contradictory conclusions may reveal the exact way in which nature does not agree with the learner's theory and can thus motivate conceptual revision. However, there have been no empirical studies that have investigated this claim. In contrast, there have been proposals in the mostly philosophical literature that tried to explain what is the underlying machinery that drives thought experiments, in the sense what determines the outcome of a thought experiment. And these are not mutually exclusive proposals. According to one, for example, thought experiments could work just like any other inductive or deductive argument, where the learner begins from some known premises and reaches a novel conclusion. Another possibility is that thought experiments could rely on a model-based reasoning, where the learner develops a mental model and runs simulations of the model, which is the basis of generating new outcomes. And along similar lines, thought experiments could rely on quasi-observational or imagistic simulations, in which case conducting a thought experiment would consist of running a simulation where the process of simulating is similar to data collection. Here in this study, in this talk, I'm not trying to differentiate between these various options. The focus of the present study is the case where the outcome of a thought experiment, no matter how one comes to that outcome, is inconsistent with other beliefs held by the learner. The question being, would the realization that one's beliefs are inconsistent with each other lead to conceptual work and belief revision? And if yes, then how does the learner decide which beliefs are true? There are many reasons to believe that noticing inconsistencies might help learning. For example, we know from prior studies that the direct comparison of representations, the comparison of exponenda with prior beliefs, and the metacognitive awareness of one's inconsistent beliefs may be beneficial for learning. But at the same time, there are many reasons why highlighting inconsistencies might not help learning. For example, learners might not even notice inconsistencies because of the inability to see deep structural relationships between various beliefs. Another related possibility is that both scientifically naive individuals and scientists seem to be blissfully unaware of harboring what appear to be naive theories and scientific theories that are in conflict with each other. And finally, even though we might have a general tendency to resolve a cognitive dissonance, there is no guarantee that the attempt to resolve the cognitive dissonance is going to be epistemically prudent. To ask whether inconsistent or noticing inconsistent beliefs can drive learning, I looked into a case study of Newtonian concepts of force and motion, that the learning of which is prolonged and very difficult. Indeed, many adults do not ever acquire these concepts or deep understanding of classical mechanics, despite having years and years of formal instruction, and despite perhaps being able to recite the Newtonian laws of forces and motion. The naive understanding that children and many adults have resembles the impetus theory of motion, where an object that is in motion requires a force to remain in motion. And once that force dissipates, the motion stops, which is exactly what's depicted in this drawing on this slide on the right, where the cannonball suddenly loses the force that pushes it to move forward, and once that happens, the cannonball suddenly drops in a straight vertical line. That is inconsistent with Newtonian mechanics, according to which bodies that are in motion do not require force to remain in motion. In the present study, I tested 575 participants who were recruited on Mechanical Turk, and they were tested in a pre-training, training, post-training design, where the pre-training included 4 thought experiments inspired by prior research and designed to elicit impetus responses. The training included 4 thought experiments inspired by Galileo, and they were designed to elicit Newtonian responses. And the post-training included the same 4 thought experiments that were given at pre-training. Here is one example of the pre-training thought experiments. Note that participants just saw the textual description. They did not see any drawings or other pictorial depictions. A train is moving at a constant velocity of 100 miles per hour in a straight line. Inside the train, there is a mechanical claw that is holding a ball, and the mechanical claw is fixed and rigid, and so it does not move as a result of vibrations. Furthermore, the claw is located halfway along the ceiling between the front and the rear ends of the car. At one point, the ball is released. Please ignore air resistance. There is no wind inside the car. And answer, the ball will fall A, behind the halfway point of the car floor, or B, exactly on the halfway point of the car floor. The response consistent with Newtonian mechanics is B, that it will fall exactly on the halfway point of the car floor, whereas the impetus kind of response would say that the moment the ball loses contact with the car, it will start losing force, that is, it is pushing it forward, and it will start losing speed relative to the train car, which is why it would fall slightly behind the halfway point of the car floor. But of course, that is inconsistent with Newtonian mechanics. The training thought experiments looked something like this. Earth spins from west to east at a constant velocity of approximately 1,000 miles per hour at the equator. Imagine yourself at the equator, standing on a flat surface facing east, where you feel that you're being pushed backwards and you need to use your own force to remain in one place. A, yes, I would feel forces pushing my body in a direction opposite from the direction in which the Earth is moving. B, no, I would not feel any forces pushing my body in a direction opposite from the direction in which the Earth is moving. Obviously, we do not feel any forces as a result of Earth's motion, which of course is consistent with Newtonian mechanics because bodies in motion do not require force to remain in motion. In addition, all participants were assigned to 3 different conditions. They were assigned to a baseline condition where they simply received the thought experiments. They were also assigned to a warning condition in which before receiving the training thought experiments, participants were asked to think about the implications of the training thought experiments and how they relate to the pre-training thought experiments. And in the third condition, the explicit inference condition, after receiving the training thought experiments, participants agreed or disagreed with an explicit inference that followed from the training thought experiments, which was that if no forces are pushing you in a direction opposite from the direction of the motion, it means that if you jump upward, the Earth's ground or the vehicle's floor will not escape beneath your feet. It also means that if you're dropped from a cliff, you will fall in a straight line. And while you're falling, you will not lose any speed relative to the ground floor beneath you. Looking first into the pre-training results, we see that the average performance was 2.32 out of 4, and broken down by item, 59%, 67, 49, and 56% of all participants gave correct answers on each thought experiment respectively, which finding is consistent with findings from previous studies. Importantly, participants who gave incorrect answers predominantly gave impetus-like explanations. The performance on the training thought experiments, in contrast, looked strikingly different. Namely, the average performance was 3.29 out of 4, and broken down by thought experiment, 67, 85, 86, and 90% of all participants gave correct answers. Now, this finding confirms that some of the participants produced outcomes consistent with the impetus theory at pre-training and outcomes consistent with Newtonian theory at training. And the question is, did the participants who offered impetus-like responses at pre-training and Newtonian-like responses at training revise their beliefs and then offered Newtonian responses at post-training? And the answer is partial yes. That is, there was no significant changes between pre and post-training for participants in the baseline condition, which is the blue bar on the left. However, responses in the warning and the explicit inference conditions changed significantly between pre and post-training, and on average, they were more Newtonian-like at post-training. This change was not driven by performance in a single thought experiment. Indeed, a series of McNamara tests showed that responses changed significantly on all 4 thought experiments, both in the warning and the explicit inference conditions. And in contrast, they did not change significantly on any of the thought experiments in the baseline condition. In conclusion, this study showed that learning from inconsistent beliefs is possible, but the study also revealed other important points, such as tolerance for inconsistent beliefs and difficulty relating inconsistent beliefs and resistance to revising beliefs, which are all points that are in line with the persistence of naïve theories over ontogenesis. And this is exactly why understanding the circumstances under which learners begin noticing inconsistent beliefs and the mechanisms that support belief change, both of which were investigated in this study, are extremely important if we are to understand the underlying processes of theory change. And I believe that this study is a step in that direction. I'd like to thank you for listening, and I hope to communicate via chat or other means after this talk. And I'd also like to thank the Mind Brain Behavior Initiative and the Stillman Drake Award for supporting this research. Thank you very much.